Okay, so now we have already done EM waves in dielectrics and insulators. So obviously the next thing that we would like to do is how do EM waves propagate in conductors? That's the question that we ask. And so we have already done Maxwell's equations in vacuum in a dielectric medium. Now we'll do in conductors. Okay, so specifically there will be loss now. And we'll also do dispersion, which would be in dielectric and not so good conductors, as we'll see. Okay, so we are following this scheme till we go to absorption and dispersion. So Maxwell's equations in conductors, the conductors, of course, they can't sustain free charges. That we know. They all go to the surface. And if there's extra charge, it simply vanishes. Okay. Uh, but we had to ignore the current, okay, in the dielectric or even in vacuum. But here we have to include the conduction current. J is equal to sigma E. So uh, in a conductor or a material, there can be free charges, obviously, but there is a current. So what we do in conductor, of course, it should be divergence of E rho f E, but we already know that rho f simply vanishes, okay, ideally for very quickly, okay, within a time constant which is given to the dielectric time constant epsilon by sigma. Since sigma is very, very high, for a perfect conductor sigma is infinity, it will simply vanish, okay, very quickly. And hence we are back to divergence of E, and we are not interested in this transient solutions. Suddenly how much, okay, we are interested in steady state solutions uh, with time. So divergence of E is 0. We say that these free charges would simply vanish. And of course, our old del cross E minus del B by del T would be there. And but now we cannot ignore the fact that there is a J which is sigma E. So the new Maxwell, while considering conductors, the changes in the set of Maxwell's equations that we need, that is different from what we had done in dielectrics, is of course this is same, this is same, this is same, but in this equation, del cross B, first thing is not no longer mu naught epsilon naught. So this is not so mu and epsilon. That's because it's material. Even in dielectric, that would be that. But in addition, okay, we have this mu into sigma term coming in from the conduction current. And then the solution looks pretty similar. We can again take uh, any of these and then take its curl, and then we'll find exactly the same thing that we did. Okay, so this will go to 0, and we will get del by del t of del cross B. Now, of course, there will be two terms. One term is as early, it was as earlier in the case of dielectric, the second order term, but there would be now this term coming from here. Okay, so in del cross E. So del cross B has now this term, and hence it has appeared here. What one del by del t here. Of course, this is equal to 0. So similarly, now we take this and I take curl of that, and divergence B, of course, will become 0. And now we'll be left with del cross E, okay, of uh, on the other side, okay, and hence we'll begin uh, ending up with the earlier term, okay, which will give rise to mu epsilon del square B by del T square. But this term is now, okay, will also give you mu sigma del B by del T. All right. So both are similar. The treatment is exactly similar as in dielectric. Okay. So we can write down, I'll write down this, removing this minus signs from both sides. So del square E is the earlier equation plus this mu sigma del E by del T. Similarly, del square B, mu epsilon del square B del T square mu. Now, what is the addition? This new first order differential in time, which is, you can see as like a friction term, okay, is a dissipative term. So these two dissipative terms now appear in our otherwise perfect um wave equation that were obtained in case of vacuum or even in case of perfect dielectric, okay, because of the introduction of this term, which is the current. So we'll look at the consequences of this in on solutions due to these terms. First, in terms of maths, okay, and then of course the physical significance of the maths. Let's get it. Let's go ahead. So wave solution in conductors, and first thing that we need to say that first order term makes it a lossy media, because there is J is there, sigma J, sigma E, which we know it will be, if there is a current, then there will be heat produced, so it will be lossy. And in that case, whatever our familiar real quantities which we associated with wave motion in dielectrics become complex. Okay, so del square E, I'm writing down again the wave equation. Now, what do? We try del square B, the same, I'm rewriting it. Now, try solutions. Okay, so to solve, as usual, we will try uh, the, okay, a complex vector. This is the complex vector. This is the amplitude, and of course I k z. Let's take oriented such that it is traveling in the z direction in the conductor. Okay, and this remains complex amplitude. So similarly, we'll take the BZT with B naught and E naught, and we'll solve for E naught and B naught in a using these two equations. So what do we get? So first term, if I put this in del square E, that will give me twice. Okay, so del square. So each time I get a ik. Okay, so it becomes minus k square. Okay, and I'll show you that k is become complex, and hence I put the complex sign on top, the tilde, to say that k is no longer a real quantity, is going to become a complex quantity. So that will, so differentiating twice with space will give me minus k square, and the first this term will give me with a differentiation with respect to time twice, so that will give me also minus I omega twice, so minus mu epsilon, okay, mu epsilon, of course omega square, so minus I omega minus I omega minus I omega square, and this term will give me, now it will, because of the first order, I'll pick up a I. Okay, so that will become minus I mu omega sigma. Okay, so this is I omega sigma is the single differential. Now you can see this is minus square quantity, but this square quantity itself is imaginary. There is a real part and there is an imaginary part. Okay. So this is complex now, and no longer corresponds to 2 pi by lambda that we had seen for the dielectric, because now it's a complex quantity. So what the guiding equation then, this wave equation simply for harmonic solutions simply reduces to this equation. That is, the exponential parts have cancelled out. So k square mu epsilon omega square plus I mu sigma omega. That is the same wave equation written in harmonic, written for harmonic solutions. So this is k is complex. This is a complex quantity, so I can always the k complex. I can write down a part which is real k, like my older k, and an I which is kappa. Here I'm using Griffith's notation, which is, let's say, kappa, and that's a quantity now. Of course, since it's kappa, this can still probably be associated with a lambda or wavelength, but certainly not a kappa. So the real part, if I just solve this, okay, that this takes square root, then I take omega out, epsilon mu by 2, and then root over 1 plus this quantity sigma by epsilon omega square. Okay, this is under root plus 1. And of course, there would be the conjugate part of it, kappa, exactly similar, except that this plus is minus 1. Okay, that is simple complex uh, arithmetic that we have seen. So K and kappa are different, of course, because of this plus 1 and minus 1 here. Otherwise, it's written in terms of it's something like K omega omega by C. So what C is now, the velocity is now a lot more complicated. Okay. And hence I can write down EI, this is K complex. That's how it is. Okay. But if this K is complex, then there is and this I here and this kappa here. If I plug this in, then I becomes minus kappa Z. Now this is a imaginary, so this is oscillatory part. This is imaginary exponential. But this part becomes now a real decaying exponential minus kappa Z. Kappa is a positive quantity, okay, and this is minus Z. So BZ is similarly. So this K becoming complex immediately gives rise to a quantity which is a real decaying exponential. So there is an oscillatory part and there is a real decay occurring also as it progresses towards Z. Okay. So amplitude B, if I include this in the amplitude, then it becomes amplitude is exponentially decaying as it progresses towards more and more Z, gets attenuated. Okay, as you would expect because it's a lossy medium. So just to show you the solution, the amplitude is exponentially decaying because of this e to the power minus kz, all right, for both E and B. There are other consequences that we'll look at it. So this is the amplitude reduces exponentially with Z, and I've already said that. Now, suppose Z is equal to, if I take such that it is 1 by E, this amplitude goes down by 1 by E, that distance, that Z is equal to 1 by kappa, then this becomes e to the power minus n, which means the amplitude goes by 1 by E. And that distance, Z is equal to D, that distance is called the skin depth. Okay, as if a metal has a skin and the electromagnetic waves can only penetrate till that much, and it loses 67% of its amplitude just in going through the skin depth, and that is why it's called skin. Okay, so the skin depth 1 by kappa is defined, so it gets attenuated and gets 1 by E of its amplitude just within one skin depth of the surface. But the K part, the real part, of course, continues to represent lambda, and V is equal to omega by K, and the real refractive index can be thought of as Ck by omega. All this is still valid, that is for K. But K tilde is no longer 2 pi by lambda. But this part can still be 2 pi by K can be 2 pi by lambda. So our old dielectric function kind of notions are preserved in this, and this is the leads to the real decay with distance. So let's look at the nature of the solution a little bit more in detail, which is dictated by Maxwell's equations. Of course, the other Maxwell's equations, as before, the divergence of E and B being 0 rule out any Z component, okay, and hence, even in a metal, it remains transverse, obviously, as it should. So, and hence, without a loss of generality, let's orient our axis such that E is along X hat. I know it's traveling in Z direction, and hence I can take the E to be in the X direction, polarized in that. And then I can write down the complex wave as directed in X polarization. Then the amplitude is uh, still complex, okay, but it is decaying with kappa Z and this the X direction. And then I can write down del cross E, and that will be minus del by del T, and that will give me my B. So BZT will be now in y hat direction, and then it, because of the del b by del t, I have now kappa by omega. All right. So e to power minus k z e to power I k z minus omega t. So I can write down E and ZT. Once I orient my axis such that it is traveling in the Z direction and E is in polarized in. So that notion of transverse, okay, and is still preserved. So again, they are thus mutually perpendicular also. That is still true. Okay. So now where is the difference? Like any other complex number, k tilde can be expressed as a modulus and a phase. All right. So let's do that. So write down as K, capital K, as the modulus of K, that is the real magnitude, and there is a phase. Okay. So I can write it on this form such that I can introduce this phase into my equation. So K, this is the magnitude, of course, K square plus kappa square. And I have already obtained K and kappa in the last slide. And on simplification, this is so this magnitude of K depends on omega, and instead of simply 1 by C, we have a little bit more complicated equation depending on again sigma and omega. This ratio sigma by epsilon omega. Okay, and the tan phi. Okay, this is the phi that I have the phase. So tan phi is simply kappa by the real part of the imaginary part divided by the real part. This, as we know, for a simple complex number. So now I can introduce that E naught, okay, is now has can have the complex amplitude. I can write down in terms of real amplitude and have a phase. Okay, so it could be the phase constant associated with E and a phase constant associated with B. Okay, so that will give rise to that I can write down as B naught e to the power I del B as k e I phi phase constant. Okay, and that would be k e I phi omega e naught e to the power I del phi. I get it from here. All right. So which means phi is now can be related to the del E and the delta E and delta B, the phase constants associated with E and B. So evidently E and B are no longer in phase. That was an important thing. In a non-lossy media, E and B were transverse, E and B were perpendicular, E and B were perfectly in phase. When E was maximizing, B was maximizing, and they would minimize and cross each other at a 0 point. And okay, now that no longer is true, and there is a phase difference which is given by this phi. Okay, we can take kappa by kappa, and this phi, that is the delta B minus delta E, is the phi. Okay, so if I take this to be positive, then according to this notation, the magnetic field is lagging behind the electric field by this phi quantity, okay, phase quantity. So the magnetic field lags behind the electric field by this angle phi, okay, which is tan phi is the imaginary part by the real part. So the ratio of the amplitudes now, if I take B naught by E naught, is simply kappa by omega, and that is from here. Okay, just k by okay, and so this quantity now depends, of course, sigma by epsilon of omega. So the real fields are then okay. In fact, if I summarize in figure all that I have concluded from here, it is exponentially decreasing. We have seen giving rise to skin depth. They are no longer in. There is a phase difference, so this goes through the minimum here, and this three goes through minimum at a different point. So there is a phase difference between the two, and they decrease. They are of course still transverse and perpendicular. And I know the relation between B naught by E naught depends on sigma and omega. Okay, of course, if this is sigma by omega is large as compared to 1, then this will be sigma by omega here. This we'll see the consequences. Okay, so you can write down the real fields as xe, it's a decaying real exponential with a uh, phase constant associated with electric field delta E, and BZT, these are the real fields, okay, pointing in y direction, B naught with magnitude going down exponentially with kappa z, and delta E plus Fi constant. Okay, so this is also a phase constant. It could be, we can set it to 0 depending on where we choose our origin, but this phi differences will always still be there. Okay, that is the way we've written down the real fields inside the conductor. Now let's take up the reflection and transmission of a conductor surface normal incidence. Okay, we have seen this for dielectric. So now I can take a dielectric on this side and a conductor on this side, conductor on this side. So let's say a plane wave of frequency omega traveling in the uh, z direction and polarized in the x direction, this x direction, approaches the interface from the left. That's the situation I described. So that it can get reflected and it can get transmitted. So as earlier, we can now write down the incident wave and the so incident wave AIZ, AIY, so exactly like that. So this is the dielectric medium. So I'm writing down K1, this is the dielectric medium 1. So K1Z minus omega t, it is traveling in the Z direction, okay, and polarized in X. So B1Z, of course, will be 1 by V1 UY, again Q1Z, it's per minus omega t, but it's pointing in Y direction. This is the Y direction, so BI is in Y direction. That's the incident wave. Now the reflected wave, okay, what changes is the K1 becomes minus, and that is, and BR now points to minus Y direction. There are only two changes only. V1 is in this direction, and hence it is going in minus K1 direction in medium 1, and in the ER is of course still polarized in X hat direction, and minus 1 by VO1 minus Q1 in minus Y direction. Is minus Y direction. So BR reflected part is pointing in minus Y direction. So what is the transmitted wave? Again, it's all seen here. You can, by seeing the figure itself, you can write it down. ETZ, the magnitude. Now it's in second medium. So I'll write down K2 Z. Okay, and it's likely to become a complex later. Okay, so BT ZT 1 by V2 UO2 I K2Z minus omega t. So in the left medium is K1 and the right medium is K2. This is the solution that I will try. Okay, dielectric. Now I'll apply the boundary condition. There is, of course, at the boundary there is no free charge, so sigma f is 0, and we assume there is no free current, free surface current at the interface. So no free charge and no free surface current, and hence we can apply what which we have done several times. The these two, the electric fields tangential components are equal, and the H, okay, the parallel component are equal. I've written down H in terms of B1 by mu1 and B2 by mu2. Okay, and of course this is always true. Okay, B1 minus B2 is equal to 0, and this is equal to 0. I've not written down 0 here. This will be equal, all right, or is equal to 0. Now, what is this gives us U1 parallel, E2 parallel. That gives us as earlier. So EOI plus EOR is EO. That is, this is EOI plus EOR. This complex amplitudes, that is simple. And this one will give you, okay, in terms of 1 by mu1, 1 by v1, EOI in the medium 1, minus this is reflected VOR as 1 by mu2, 1 by v to EO2. So this can be simplified, okay, to write down EOI minus EOR in exactly the way we did in dielectric, in terms of a constant, uh, uh, not a constant, as a parameter beta tilde, which is a complex now, okay, and then we can solve for EOI and EOR, okay. So I do that. Of course, In non-magnetic material, we typically take mu1, mu2 is equal to mu naught. That makes life simple. Both are non-magnetic. Then EOI minus EOR is this beta tilde, okay, and that is nothing but mu1, v1, mu2, omega, but now K2 is complex because it is now in the conductor, all right, and hence beta is complex, K2 is complex. The solution will look formally similar to alpha and beta as in the normal incidence case. We had done it for the dielectric case, okay, but the formula looks similar, but this beta is now complex because K2 is lossy, okay. So this is mu1, all right, okay. So this is EOR 1 minus beta 1 plus beta EO2, exactly similar. Now if I take for a perfect conductor, if sigma is infinity and K2 is infinity, then of course beta is infinity, and EOI plus EOR simply minus EOI, and there is nothing transmitted, okay, which means everything is reflected, total reflection, and since this is minus, there's a 180-degree phase shift. So if the conductor is a dielectric wave coming and hits a conductor, okay, as in the mirror, okay, it's glass and then travels inside the glass and then hits the silver at the back of the mirror, okay, and it goes, everything is supposed to, if it's a perfect conductor, everything is reflected back and with a 180-degree phase shift, okay. So that is minus EOI, and you get really a mirror, okay. So that's normal incidence. Only thing to note that this is indeed looks similar, but they are all complex quantities, okay. That is what I said, that once there is a lossy media, then all our familiar quantities becomes complex. So let's go to the complex, look at the complex propaganda vector, this propagation vector, the frequency dependence, okay. Then since there is frequency dependence, that something which is a good conductor can become at some frequency good, in fact, bad conductor to good insulator, okay. So there is now the concept of what is conducting and what is insulating would depend on the frequency of the wave. So, and where do we start from? Our wave equation in harmonic solution, okay. The complex K propagation vector square is nothing but mu epsilon omega square plus I mu sigma omega. This is effectively the wave equation, okay, for the harmonic wave solution. Now, this one is like, you can see mu and epsilon like the velocity, okay, 1 by v square. So this is the origin and displacement current. So this part comes from the dielectric-like behavior, whereas this part, okay, depends on sigma. So this is more like conductor-like. So, and origin and conduction current. So assuming sigma and epsilon are constant, the omega they are not. Later we'll see. But suppose we assume that sigma and epsilon uh, in the range of frequency I'm interested in at the moment. If I take that to be constant, even then the ratio, I can take that ratio, okay. Uh, okay so when is a material good or a bad conductor for EM waves? Okay, that's what we are asking. So it depends on the ratio of these two terms, on the imaginary part to the real part. And what is that? That is, you can see, divided by this. So sigma by epsilon omega. Okay, so you can see I have taken an example of a humid soil. Okay, particular humid soil, depends on humidity, of course. Is relative permittivity is 30, and it is resistivity is like 10 to the power minus t ohm meter, ohm meter inverse. Okay, so it is ohm meter. So conductivity is 10 to the power minus s by m. So now I plotted sigma by omega by epsilon, this quantity. This quantity is conductor-like behavior, okay, with ratio by dielectric-like behavior. So for low frequencies, okay, you can see that it can behave like a good conductor. This is a huge range of this ratio, 10 to the power minus 4 to 10 to the power 6. 10 orders of magnitude of this ratio I'm talking about. And the frequency, I'm also 10 orders of magnitude, 1 to 10 to the power 10. Okay, so it's a huge range of frequency. And if I do that, then I can calculate, then in this range, sigma dominates, and hence it's a good conductor. And as omega increases, of course, this will make it low, and then this will become a good insulator. There's hardly any conduction because this quantity is going to lose out. So it will behave more like a dielectric. Okay, so the same material can, and with sigma and epsilon roughly constant within the range of the frequency, then also at higher frequencies, the dielectric-like behavior would dominate over the conductor-like behavior. And this fact is used routinely to characterize all kinds of materials, okay, from biological, electrical materials, and even geological rocks, and so on and so forth, and all kinds of materials. Okay, we'd like to figure out what is the frequency dependence of its conductivity, uh, and the ratio between the conduction current and the uh, dielectric-like displacement current. Okay, so how is it in real materials? Okay, so how do you, so often in characterizing, so we do a lump circuit model, okay, consisting of R and C. That is basically the conduction current can be represented by resistance, okay, and the displacement current by capacitor. So what do we do, that take let's say this is my material. Okay, this shaded portion is my material. You can think of it has a resistive part, and there is a capacitive part. And then when I apply a voltage, close the switch, then there will be a resistance current, and there will be a current with this if it is AC, of course. Okay, if it is DC, then of course this is blocks out. Okay, so take the material, and then if I allow a V is equal to V naught sine omega t, then of course V naught sine omega t by R would flow through this. So there is a DC or low frequency conduction current, okay, which will be proportional to sine omega t, correct? Okay, that will be in phase with the applied voltage. But this would be dq by dt, and hence c dv by dt. So it is c dv by dt, and it is high frequency displacement current. Okay, so this will dominate. So c, so if I differentiate dv, so I'll get c omega. So this current depends upon c omega. Higher is the current, higher is this current through that. In fact, at very large current, this will short. Okay, and you will not see the whole circuit will get shorted at high frequency, and you will not see the effect of this resistance. Okay, and but this is proportional to C and omega cos t. There's one thing is that the difference between the two, the 90-degree phase difference between the two currents. Okay, and quite often, so at a 90-degree phase difference between the two currents, and this is how we use to distinguish between, in any material, how much is the conduction current and how much is the displacement current at any particular frequency. Okay, because then you can check out which is what component of the current is 90-degree phase shifted from my source voltage. Okay, and that is the displacement current. So it is most often used to measure the capacitance. If I know omega, okay, if I know the frequency of my signal, and if I find out my V naught, if I know my V naught and omega, I can find out the current which is 90-degree out of phase, and from there I can calculate from the magnitude I can calculate the capacitance. So capacitance is dynamically figured out by simply measuring the current which is 90-degree phase shifted out of the voltage that is applied. Okay. Now I can ask you, what will happen instead of this sine omega if I give a pulse, okay, which is a pulse which suddenly goes to a very sharp rise, 0 to V naught and V naught to this circuit. Please work that out. Okay. So if I give this pulse instead of this, if I give this pulse here, and connect it to oscilloscope with a resistor, what kind of current that I will see in the oscilloscope screen. Okay, please uh, figure that out. Okay, and that's something that you will see in the lab whenever you are using a pulse and circuits involving resistance and capacitance. So in summary, okay, we have discussed EM waves in conductors. This is the this actually this icon sort of summarizes everything that we want to say about EM waves in conductors. Okay, so conduction is a lossy media. So conductor is a lossy media, and EM wave amplitude decreases exponentially. It reduces to 1 by E of its value uh, in one skin depth. That's how we define our skin depth. The propagation vector becomes complex. It was real in and dielectric. I'm just reminding you. E and B fields are no longer in phase. Magnetic field lags behind by a phase constant. It's phi, which is tan phi is kappa by k, as we just figured out. The consequences of this are many. A perfect conductor, as we saw, reflects back the entire wave with a phase shift of 180 degree. Okay, and the ratio of the conduction current to displacement current is dependent on frequency as sigma by epsilon omega. That's a learning that we have done by looking at EM waves in conductors. At high frequencies, the displacement current dominates over conduction current. Okay, and a good conductor at low frequency can become a bad conductor at high frequencies. Okay, these are important mental notes to keep as summary of our study of electromagnetic waves trying to travel through conductor. Thank you.